Hey, it's Mr. Lum again, and we're going to be working on the January 2003 provincial exam, and we're going to be focusing on Unit 4 questions today. So, we're going to be doing question number 23 is first. And it says, which of the following represents the neutralization reaction between calcium hydroxide and hydrochloric acid? Okay, so what we're going to be looking for is an equation that has like acid plus base makes salt plus water. Okay, so this one is not, this is just the self-ionization of water. This one is the crystallization of CaCl2, and this one down here is the ion form, or the complete ionic form of this right here, and that's not what we're looking for. We're looking for calcium hydroxide when it's solid, so it's going to be calcium hydroxide when it's solid, plus hydrochloric acid, right like this, making water and a salt. So this is the answer that we want. Okay. The next question says, which of the following solutions will have the lowest electrical conductivity? So, lowest electrical conductivity means when you have the least amount of ions. So let's take this, underline it, and write. So if you have low electrical conductivity, that means you have a low concentration of ions. So which of these has the smallest concentration of ions? Well, right here, even though this is not an acid or a base, it is very, very, very soluble. So this one is going to be making Na plus and NO3. In fact, all of this is going to be turning into ions. So what you're going to be having is, you're going to be having 1 mole of Na plus, and you're also going to have 1 mole of NO3 minus. So all of this is going to be turning into ions. So not this one. Now, this one is also very, very soluble, as well as it's also a strong base. So again, this one's going to be turning into 1 mole of Na plus and 1 mole of OH minus. Now, here's 2 right here, Hi and H2S. Hi is a strong acid. So this one's a strong acid. And a strong acid means that 100% of this is going to ionize. So again, you're going to have 1.0 moles of H plus ions and 1.0 moles of I minus ions. Okay, so these ones aren't it. So we obviously know it's going to be this one. Now, why is this one H2S? Why is this the correct answer? Now let's take a look at our table. So here is our acid-base table, and if we look for some of these things right here, we can see, well, first off, we can see Hi is right here, okay? And we can see that it's very, very large Ka, and therefore it's very, very strong, and it's going to 100% ionize. Now let's look for H2S. There it is. H2S. Okay, and it is a weak acid. So even though this is all going to dissolve in water, only some of it is going to ionize. Only some of this is going to turn into H plus and HS minus. And since this number is much less than 1, very, very little of it is going to turn into H plus ions, and very small amount is going to turn into HS minus ions. Most of it is going to stay as H2S, which is not an ion. So going back to this question, right here, 100% of this is ionizing, 100% of this, and this one is ionizing, and only a small amount of ions are going to be made for here. Okay, a very, very small amount, much, much less than 1.0 molar concentration of ions in the solution. Okay, so 24 is B. Let's move on to 25. It says here, consider the following equilibrium equation. Which of the following statements is true? And it's asking products favored or reactants are going to be favored. So what we need to do is we need to figure out here first which ones are our acids. So as H3O plus turns into H2O, it loses a proton. Since it loses a proton, this one right here is our acid. Okay. And in the reverse direction, H2CO3 is turning into HCO3 minus, and this is also our acid on the product side. And this makes H2O right here. This is our base on this side, and this is our base on this side. Okay. So now which one is going to be favored? Well, what you can do is you can look at and compare the strength of H3O plus and look at the strength of H2CO3. So let's take a look at what are the Ka values of H2CO3 and the Ka value of H3O plus. So H3O plus has a Ka value of 1.0, and H2CO3 has a Ka value of 4.3 times 10 to the minus 7. Okay, so we're going to memorize these two numbers, 4.3 times 10 to the minus 7 and 1.0. So what we're going to look at is we're going to look at KEQ, and that is going to be Ka of a reactant acid divided by our Ka of our product acid. And therefore KEQ equals Ka of our reactant acid, which is going to be, here's our reactant acid again. I'll just write a little A right there for our reactant acid. And if we remember it, our Ka for that acid was 1.0. And our Ka for our product acid was 4.3 times 10 to the minus 7. So if we calculate KEQ, KEQ equals 1 divided by 4.3 times 10 to the minus 7, and that equals a very, very, very big number. Well, it equals, well, we'll just make it 2 sig figs, since these are 2 sig figs. Ran out of room there, but it's actually KEQ equals 23, 2, 3, 4, 5. And so what we see is KEQ is much, much larger than 1. And so therefore it means that products are favored. Okay, so it means that products are favored. And it means that H3O plus is a stronger acid than H2CO3. And this is our correct one. Now, A says H2O is a stronger acid than H2CO3. That's not true. H2O right here is acting as a base. So H2O is not acting as an acid at all. H2O is acting as a base. So, since products are favored, you know it's going to be A or B, and H2O is a base, so this is not correct, and this one is. So 25B. Okay, let's move on to 26. Which of the following factors of an acidic solution would affect its pH? So, the strength of the acid. Yes, this one affects pH. So, for example, 1.0 HCl is going to have a much lower pH than 1.0 HF. The reason why is because HCl is a strong acid. HF is a weak acid. This is going to have a lower pH. Okay, so strength of the acid, absolutely, this is going to affect the pH. The concentration of an acid, yes, that also affects pH. Again, let's do an example. 1.0 molar HCl is going to have a lower pH than 0.1 molar HCl. Okay, so the pH of 1.0 molar HCl is going to be 0. And the pH of 0.1 molar HCl is going to be 1. Okay, so concentration of the acid does affect the pH. And what about temperature? Yes, it does. Okay, remember how strength and all that kind of stuff is affected is that they have these Ka values. Ka is going to equal your products over your reactants. And Ka, the only thing that's going to be changing Ka, or the amount of ionization of like a weak acid like this, like HF, is going to be dependent on temperature. Okay, so temperature is going to affect the pH. Even if you think about something like Kw, how that equals your concentration of OH minus times your concentration of H plus, and how that is going to be H2O plus some energy makes H plus and OH minus. If you increase the amount of energy, you're going to be increasing the H plus and OH minus ions. Since you'll increase these things, well, your pH is going to decrease as well as your pOH. But the point is that temperature will affect the pH as well as the pOH. So all three of these, yes, yes, and yes. Okay, so the answer is 26D. And for 27, consider the following equilibrium, and we have the ionization of water right here, and it says what changes occur to H3O plus and pH when NaOH is added. Okay, so we add NaOH, it increases this concentration right here, which then makes this reaction shift left, and therefore this concentration decreases, because for up here, Kw equals H3O plus times OH minus. Or in other words, 1.0 times 10 to the minus 14 equals these two concentrations. Now, normally in water, there's something like 1.0 times 10 to the minus 7 times 1.0 times 10 to the minus 7. Now, if this was increased, this needs to decrease in order for Kw to still equal 1.0 times 10 to the minus 14. H3O plus is going to decrease. Okay. Now, if H3O plus decreases, what happens to pH? Well, as we know, H3O plus is an acid, and that is pH is a measurement of the concentration of H3O plus. All pH is taking the concentration of H3O plus and putting on a logarithmic scale. So if this decreases, then pH is going to increase. For example, say if we had a concentration of H3O plus that is equal to 1.0 times 10 to the minus 7. Okay, the pH of this is going to equal to 7. Now we take something else like H3O plus, and we're going to make this a smaller number. So a smaller number than this is going to be something like 1.0 times 10 to the minus 9. Okay, this is 100 times smaller than this number. And if we were to calculate the pH of this one, it would be pH would equal 9. Okay, so as the H3O plus decreases, the pH increases. Okay, so that's going to be our correct answer right there. And moving on to question number 28. And it says the ionization of water is endothermic. How is Kw related to the temperature of water? Okay, so as I wrote before, let's write H2O plus some energy, since it is endothermic, forms an equilibrium with the self-ionization. Okay. Now, it says, how is Kw related to temperature? Well, Kw is going to equal the concentration of H plus times the concentration of OH minus. Kw is going to increase if temperature increases. Say if we make temperature increase, okay, this reaction is going to shift to the right, and therefore H plus is going to increase and OH minus is going to increase. If these two numbers increase, Kw is going to increase. So Kw will increase if temperature increases as well. Okay? If Kw will decrease if temperature decreases. So let's look at some of our things right here. Kw remains constant as temperature decreases. No, the only thing that's going to be changing Kw, Keq, Ka, and all those kind of things is temperature. So this is not a correct answer. Kw increases as temperature decreases. No, we said if temperature increases, Kw increases. And so that makes this one wrong as well. And the only one that's right is 28A. So number 29. Which of the following represents the dissociation equation of a salt in water? This is kind of an interesting question. It's kind of like a solubility question rather than a Unit 4 question. But anyways, let's take a look at this one. So a dissociation equation means when you have a ionic solid, I guess we'll write a little definition right here, ionic solid turning into ions. Okay, so that's your dissociation equation right here. So here's an ionic solid, and it's turning into ions. there's a correct answer. This one is ions turning into a solid. This answer, this is a crystallization reaction. That's crystallization, so this one's wrong. HCl plus KOH, this is a neutralization reaction. That's a neutralization reaction. And Na solid and H2O makes a little bit of a bang, and you're producing sodium hydroxide and hydrogen gas. This is just a chemical reaction. So our answer is 29A. Okay, nice, quick, easy one. Number 30. Which of the following represents the equilibrium constant expression for the hydrolysis reaction that occurs in NaF? So we're looking for a hydrolysis reaction. Now, hydrolysis reaction is when you put a salt in water and one of the ions is going to be reacting with water. So let's take a look at NaF right here. Sorry, let me finish my salt in water, and the ions in that salt are going to react with water to produce an acid or a base. So let's take a look at NaF. Now Na is a spectator. Okay, so this is going to be Na is a spectator. If you remember your spectator ions for cations, spectator ions include all spectator cations include everything from column 1 and column 2. So in other words, your alkali metals and your alkaline earth metals. So column 1 and column 2. And Na is in column 1. So that's how you know Na is a spectator ion. F is not. Okay. So F minus is going to react with water, and it's going to be making HF and OH minus. Okay, and so your K value is going to equal products over reactants. You do not put water into the equation because water is a liquid. Everything else is aqueous. So here's your equilibrium constant expression. Now, since you're making OH minus, it is not Ka. Okay. Since you're making OH minus, you're going to call it Kb. So here is your answer right here. Now, some other things that some people will be picking, might be picking, is this one, KEQ. And yes, this could be an answer right here. However, is that one is NaF is going to be this is not going to be forming an equilibrium. This is going to 100% dissolve in water because NaF is is very soluble. But also this reaction right here is kind of going to be your KSP, your solubility product reaction, if you're going to make a saturated solution of NaF. And that would be, this is more like your solubility product kind of reaction right here. This is not a hydrolysis reaction. Kw, this is your self-ionization of water. This is not your hydrolysis of F minus or fluoride ion. And so here's your answer right here. Now, if you have a hard time finding making making the connection between 30A and how did I come up with this formula right here, well, you don't have to memorize any of this kind of stuff, because you can just go to your Chem table and it gives you the reaction rate here, right here. So you can just go, oh, there's F minus. What does F minus make in the reverse? Well, you know it's going to be reacting with water. You know that it makes HF. And so what is left over? OH minus. Okay, so you can figure out what are the products and the reactants of everything using this table. Most of your answers are going to be in these tables, so make sure to use these tables a lot. Refer to them a lot when you write your tests.